All right, well, welcome everyone for part 2 of the Building Enclosure Best Practices webinar. We'll just get started right away. We did add some time onto the webinar today, just so that we could review what was missed last webinar, and then just provide us a little bit more time to go through the mock-up. So for those of you who haven't attended one of our webinars before, my name is Jenna. I work as a Built Environment Initiatives Coordinator with the Community Energy Association. I'm just going to give a quick introduction and then pass things over to James Bourget with RDH Building Science to take us through some best practices for high performance building. All right. So I'm joining from what is now known as Nelson, but for thousands of years has been the traditional homeland of the Snakes Nation, the Silks Nation, and the Ktunaxa Nation, and is home to the Métis and many diverse Indigenous peoples. I like to express my sincere and deep respect and gratitude for their generations of stewardship over the waters, mountains, and forests of this area and across Canada. As part of CEA's commitment to truth and reconciliation, we recognize the importance of amplifying Indigenous climate leadership. So I wanted to start off today's session by highlighting a project aimed to equip all community homes with heat pumps. So Sikadak is a community of the Gitxsan people in the Hazelton area of the Skeena country of northwestern British Columbia. The community is located on the west side of the Skeena River between Hazelton and Kispiox. It is a small and vibrant community that seeks healthy, safe, and positive development that is sustainable for future generations. The Sikadak Band, also known as the Glen Vowel Band, received $300,000 in funding through the BC Indigenous Clean Energy Initiative to help improve the community's energy efficiency. And they're using this funding to install heat pumps in 70 community homes. And with the completion of these installs, all 75 homes in the community will have a heat pump. So if you'd like to learn more, you'll see at the bottom of the slide there a couple of just different links that you can go at and read more about the project. All right, for those of you who are joining us for the first time, welcome. The Community Energy Association CEA is a registered charity and nonprofit. We're committed to advancing bold climate and energy action by local government and Indigenous communities. So we're proud to be the only nonprofit in BC dedicated exclusively to supporting these communities in their efforts to tackle climate and energy challenges. So CEA recognizes that the built environment is a significant contributor to community greenhouse gas emissions. So by addressing this sector, we can achieve meaningful emission reductions, strengthen community resilience and energy security, and enhance the comfort, health, and safety of our homes. Perfect. So at CEA, we coordinate and deliver a variety of activities and projects aimed at enhancing contractor capacity across BC. So today's webinar is brought to you by Building a Legacy North and the Kootenay Clean Energy Transition Projects. So since 2021, Building a Legacy North, a partnership between CEA and the Canadian Home Builders Association of Northern BC, has supported the implementation of the BC Energy Step Code and Zero Carbon Step Code in Northern BC. Building a Legacy offers training and resources to the building industry and local governments focusing on high performance construction and retrofits in cold climates. The Kootenay Clean Energy Transition, or KCET project, was created to address evolving trends in energy efficiency, renewable energy, and home comfort. So through KCET, CEA helps Kootenay and boundary communities transition to a more energy efficient and healthy future by providing training and capacity building sessions like today's webinar. So we're grateful for the generous support of the organizations listed at the bottom of this slide, which enables us to offer this free session featuring insights from industry experts. And then for a full schedule of upcoming events and webinars on high performance building, you can visit our website at communityenergy.ca/news-events. All right, just a quick plug for those of you who are involved in retrofits. I'd just like to introduce you to the Home Performance Contractor Network. So this network is perfect for those working on heat pump installations, window and door retrofits, or installation upgrades, especially if your clients are looking to access provincial and utility rebates. So by joining, you'll gain access to industry-specific training, and then upon completion of the training, you may qualify for subsidies and reimbursement for course costs. So if you have any questions about the Home Performance Contractor Network, feel free to reach out to the Home Performance Stakeholder Council directly by using their info@ email address on the slide there. All right, and then just a couple of housekeeping items before I pass things along. CEA, we're dedicated to offering educational opportunities to all, no matter their current knowledge or experience level. So we prioritize creating a safe and welcoming environment for attendees to engage and participate. So if you have questions for James as he goes through his presentation, feel free to raise your virtual hand. You'll see it on your screen under the reactions button. Or go ahead and put your questions in the chat and I can ask James directly for you. We are recording this webinar today, and we'll be sharing the recording along with these presentation slides to you via email by the end of the week or early next week. And then if you are collecting continuing professional development points through BC Housing, we will be sending out a confirmation of attendance email to folks who have joined us for the full duration of the call. So you should see that coming out as well by the end of the week. And that's it from me. It's my absolute pleasure to introduce once again James Bourget, Principal and Construction Specialist with RDH Building Science. So James brings over 40 years of extensive industry experience with a distinguished career spanning 2 decades in both the construction sector and as a building enclosure consultant. So his expertise encompasses a wide range of specialties, including condition assessments, design and detail development, and field review, particularly on existing building projects. So with that, James, I'll pass things along to you. Thanks for joining us this morning.
Thanks, Jenna. Okay, welcome everybody. This is part 2 from started on November 12th, part 1, and today we're doing December 3rd, part 2, and I have a boatload of stuff, okay? So I'm going to be moving along fairly quickly. I believe you all get a copy of the slides anyway, but I want to expose you to a lot of stuff because, well, there is just a lot of stuff when you deep dive into assemblies. Material being used for reference, continuing education and training purposes only. Okay, you need to make your own site-specific decisions and follow laws, codes, and regulations, etc. This is legalese blurb that I have to put in front of the slides. Okay, you can read that. This is not, you see it here, it doesn't mean you go and do it. It means you could do it, but you need to know by each site its own conditions. Okay, this is going to talk about the building science and the fundamentals. The agenda for today is I'm going to do a quick recap on building science fundamentals for those who did not come to part 1. Those that came to part 1, it's just a refresher. I'm going to breeze through that, and I've kept it very light and simple. Talk about some environmental loads, mock-ups. We didn't get through the slides on the below grade in part 1, so I'm going to blast through them. I went through the physical review of it, and so this will be a nice recap, I believe. Then I'm going to look at a wall to roof with a vented attic roof. We're using an exterior air barrier approach. How do you transfer the exterior air barrier to the attic when the air barrier in the attic is actually the vapor barrier, the poly, so it's air barrier by default, okay? It's kind of the red herring and a bit of a problem. I'm going to show you unique ways of addressing that. Quite simple. And then we're going to look at a flangeless window installation, high performance, no flanges. As we move forward, that'll be kind of the way the industry is going to go. And with all of these, you get various renewable detailing aspects, improved air tightness, thermal strategies, climate adaptation, fire resiliency. All these things fall into place because we're going to start putting things in a proper location. So what is a building closure? It's an environmental separator. Separates the built environment, where you are, the natural environment. Quite simple. Building science apply the laws of nature to manage the heat, air, and moisture across the building enclosure here by climate zone in our province. And we have different climate zones and different requirements. Pretty straightforward. Here's a look at the climate zone map for British Columbia. You can see there's different environments, varying interior environments, and you need to build accordingly. So that's straightforward. What the building closure does, it just separates the inside from the outside. Okay, it's really that simple. Okay, it keeps warm air in, keeps cold air out. Okay, or vice versa, depending summer, winter. But it really depends on how it's designed, how it's constructed. All right. What we've done in the past, not necessarily is suitable for the future. Environmental loads are 5 critical barriers. All right. And so the air barrier is a direct or indirect relationship with all the environmental loads. It's kind of like the king of the critical barriers. Very important. You look at thermal, it has a relationship with 3 out of 4. You look at vapor, it deals with vapor. Water deals with water. So at the end of the day, get the air tightness, then work on your thermal, then do your mechanical. Okay. Envelope first. Traditional wall assembly here, you can see that there's a little bit of insulation on the outside, keeping the sheathing warm, but the vapor barrier goes on the warm side of the insulation. Full stop. That's it. But it can also be the air barrier. In the past, we've been taping a poly and making it the air barrier by default. That's the only reason you tape the polys, because you're using it as an air barrier. If it's vapor barrier only, you do not need to tape your poly. It's a function of area elapsed. 95% covered, 95% effective. 100% covered, 100% effective. Vapor to drive is one-dimensional. Air leakage is three-dimensional. Hence taping of an air barrier. I look at nature. We should look at nature. Thermal performance by resilience in nature. Nature has a handle on all the climate zones. Interesting. So how does nature stay warmer and how does your body stay warmer? Well, I asked everybody in the forest and they said, well, we kind of got this little inner layer of fat, subcutaneous layer, and some skin and some fur. So we put some controls on the outside. I asked Buddy, he said, hell, it's cold out, I'll buy a ski jacket. That's it. Okay, put the controls on the outside. You think to yourself, well, you put all the controls on the outside, how should your home stay warmer? It's organic. Animals, humans, we're organic. How do you separate them? So from the inside, the outside, or both? Well, this is off my property. There's a big black bear there, and he's walking up towards me. And I'm sitting there thinking about this wall. And my next class, and he says, well, what are you thinking? I said, well, I'm looking at this wall, and I'm thinking that if I took that insulation and it was like the subcutaneous layer of fat under the skin, and I took the plywood, which is the skin of the house, and I'm considered it the skin like on animals and humans and everything. I said, then I take the outside, the thermal and the cladding, and that'd be like the outside fur. It's like, it seems both you and the wall are split insulated. Well, that's right. And yeah, and it works for me. And I make this tongue in cheek because the answers are so glaringly obvious. All right, that stuffing a wall is habits of the past. Don't apply to the future. Don't apply to high performance. Not effectively, not without risk. If you build and follow the guide led by nature, you can build without risk for assemblies that are highly durable with no failure mechanism. Interesting. More to that point, more interior insulation means colder sheathing. Colder sheathing means higher condensation risk. Means you need to have the ability to dry out. Many climate zones don't have rain screens, so how does it dry out? It's kind of like a snowball of trouble. And so we hope it works out. Hope's not a good play. You look at the climate zones, you go up, it's just a little graphic to get your head wrapped around a little bit, saying, oh my. So the colder it gets in the climate zone, the colder sheathing gets, the higher the condensation potential. Condensation from what? Well, from air leakage. Air leakage is never zero. And if it touches cold sheathing, that sheathing will be below dew point for your interior air. So it's going to get wet and damp. And can it dry out? Maybe. Is that the best way to build? No, I don't think so. So here's a case study from a northern climate zone, 5 years old, 0.5 air changes, super fat wall, north wall, it's 5 years old. So you can see the vinyl siding is right on the sheathing, and if it's getting damp, how's it dry out? Vinyl's a big barrier. You got big barrier on the inside, you got big barrier on the outside. It's just a potential for issues. This is happening. And the problem with buildings is they fail over time, not right away. So, oh, well, I never see a problem. Well, I do. So more exterior insulation means warmer sheathing. So very much, if you're summertime, you wear a t-shirt, fall time, you wear a sweater, winter time, you wear a jacket. Change on the outside conditions, you just put on a sweater. And the more fat of the sweater, the warmer you are. So the skin is the plywood of a home. So the plywood's warm, and so any air leakage or moisture won't condense because it's warm. And to that point, if you take a -10 design temperature, like somewhere down on the coast, something like that, and you apply no exterior insulation, and you just have bats, the sheathing's sitting somewhere, well, at -10, it's going to be really cold, okay? And so it's below dew point. Dew point for interior environments could be somewhere between 4 and 9 degrees in the average range of human comfort per ASHRAE, which is 18 to 27 and 30 to 55% humidity, okay? But in that zone, 4 to 9 is a fair assumption. So I put 1 inch on the outside. It warms up the sheathing. It's still a bit light. I put 2 inches on the outside. Now I'm sitting around the 5.5 degrees. That's pretty good, but it depends on my interior environment. I could still get condensation. And depending on the type of insulation I put there, I would like it to be vapor open so that if I do get some wetting, it'll dry out. I said, well, what if I put 4 inches on? Well, all of a sudden now, my chance of condensation in that sheathing is virtually zero. And I have a wonderfully resilient wall assembly that's fire resistant, water penetration resistant, increased airtightness. All these wonderful things happen because we're starting to put the controls on the right side like nature, okay? Now, if I put all on the outside, well, now the plywood's inside the building, okay? So you can go look at furniture from the 14th century at the museum because it's inside the building. Well, your building is now inside the building. There's no failure mechanism for your wood frame. For everything you go backwards from there increases your risk to the point where we've been stuffing walls, and that's the most high risk assembly you can build. The below grade air barriers, we talked about this, and we didn't get through the slides. This is what we typically using is seal polyethylene over insulation, or if you got radon, then you got the radon underneath with airflow and different mitigation systems. But regardless of that, that's a typical approach below grade. So some below grade considerations that we're going to look at, and I talked about, is continuity of the controls. Thermal mass is a big one. So you put the insulation on the outside, you got all that concrete below grade is going to absorb heat. The insulation outside of that's going to hold the heat into concrete. And then when you dial down the heat in the room, it gives it back to the room. It's kind of a pretty simple concept that we put poly and bat and insulation on the inboard side, and we disregard that thermal mass. Well, that'd be like building a fireplace or a barbecue and not putting any thermal mass around that. It's kind of not, well, silly. We'll look at some transition detailing. So this is the below grade assembly mock-up. I didn't take you through the slides, so I'm going to kick you through because we've already talked about it. So I'm going to take you through these slides here, okay? And so there's a waterproof for damp proofing is required. That's on the concrete, okay? So each sentence will be followed by a green arrow, so you can follow my squirrel, okay? That's how I set that up for you. And so XPS adhered with polyurethane spray foam, so you can glue that to the membrane. That's quite common. All right, right there. Drain mat mechanically attached, right there. And they attach it right to the foam, and I'll explain that in the next slide, how that happens, okay? Flashing membrane tape over the drain mat to ensure it's not contaminated, the core and debris behind it and all the rest. So you can see that that's working. And I look here, I got a self-adhered membrane transition from below grade to above grade. So the concrete turns into framing. So I have a self-adhered membrane connecting the concrete to the framing, and then I transfer the exterior air barrier into that concept. So below grade mineral wool, this is a fire rated assembly. I have 2 feet simulated 2 feet of mineral wool below grade because I have seen on burnt sites where people have lost homes and cabins, etc., where the ground actually drops significantly because the biomass becomes a peat fire. So you're protected for 2 feet below grade also. Then the XPS starts down below that. Prime the mineral wool. So you can use a aerosolized peel stick primer, spray the mineral wool. It becomes hard and crunchy and becomes easy to put membrane on. Otherwise, it's like putting Scotch tape on a cat. Doesn't stick so good. It's all fuzzy and, well, it doesn't work. Now it works fine. So this is how I stick on the insulation. I can also adhere the mineral wool this way. The same kind of thing to do for roofing, adhered roofing systems, okay? Well, this is just a vertical wall, adhered wall system, okay? So I use a polyurethane spray foam adhesive. Drain mat, you can buy drain mat augers. They screw right into the insulation. They hold extremely well. You can use rock slinger, backfill, you do whatever you want. It makes a wonderful drain mat attachment. And then primer, I just spray the elastigirl primer on there. It becomes crunchy, or it could be a Henry's primer. I don't care whose primer, whatever it is for the peel stick you're using. So the below grade assembly detailing, flashing membrane tape installed. So this is to direct moisture out of the assembly. That's right here, okay? That's part of the code thing, that if water can get to the structure, you need a means to dissipate it to the exterior. I'll tell you right now, when you exterior insulate, no water's getting to the structure. However, we have to follow along for the time being because the requirements are and the building code are not perfectly harmonious at this time. Okay, I could share some stories of testing, but in the meantime, it's simple enough to follow along. So the sheeting membrane laps over and taped to the self-adhered membrane. That's right here. So it's shingled. That's what's required in the building code, that it be shingled at least 50 millimeters, 2 inches. Okay, that's what we've done. So water would drain outward. That's nice. So now here, I've got an EPDM gasket for an electrical I threw in a wall for fun. That's sitting right here. That's the electrical penetration detailing. So the funny thing about electrical boxes, for example, they're 2 inches. Well, range screen 3/4 and cladding is usually 1.5 inches. So I need to recess the box 1/2 inch. So I simply trace the box on the insulation. I take the plug out of it, slice a 1/2 inch off it, put the plug back in, and put the a little plywood plate that screws into the wall assembly. Then I attach the box to that plywood receiver, okay? And the plywood receiver terminates a 1/2 inch shy of the finished plane of the insulation. and you can see that it fits the box perfectly. All right, so that's a 1/2 inch notch in the insulation to receive a plywood receiver that you see on the right-hand side. And 2 layers of staggered insulation in each direction. And then that's a 1/2 inch plywood receiver. The receiver's there because you got flashings and metals. It's very challenging to fasten the back leg of metal through the insulation. You can't put the metal on the plywood because then you got a thermal bridge. And if you do that fastening through the insulation, you're going through the air barrier. And many times you have to make adjustments, but you can't take those screws out. So if you put a receiver plywood fastened through the air barrier, you make the compression seal and it never comes off, it stays. Now you can play games with your flashing with short screws that never penetrate the air barrier. So here I've taken and I ran my cordless skill saw along the plywood. I cut a 30-degree, a 3/4 inch deep cut in the mineral wool above the plywood, right there. I installed sheeting membrane. I tucked it into that saw cut, so it's shingled. One of the things you have to understand is this mineral wool is hydrophobic. Water will run down, so now it just runs off. So I just tucked it inside there. Very simple to do. Just different ways of looking at things. 3/4 by 3 inch PT strapping installed for the cement board base right here. Cement board or parging installed here. It could be parged after, whatever. Now you get to this point here. You got a base wall flashing. You see the base wall flashing has a little cut right here, right? Well, that tucks into that reglet right here, just like the Tyvek did. So it becomes a shingle. This is incredibly simple to do and highly effective. I can pour water here all day long and no water will ever get behind anything. And so now I've got that done right there. Install perforated metal insect screening strapping right here. So cladding installed, electrical trim. So there's the electrical box that we had that was set into insulation. I have a trim that's got a notch in the backside to slip the hardy in behind. And it's completely serviceable. I can remove the trim. I can remove the box. I can do whatever I want with that electrical. Look at behind there. So here's a below grade detailing. I'm looking from the backside. I say, okay, well, I got some bad insulation. Yeah, that's cool. Remember, I got insulation on the front side of the concrete. I also got insulation on the front side of the wall and inside the wall. I got a structural tie down shown right here. These are Simpson, tension tie down. You attach it into a double stud. Quite simple to do and doesn't interfere. One of the things that we see is typical tie down straps that are not conducive to exterior air barrier applications. And Shazam. You look at this and go, what the heck? What am I supposed to do with this? Okay, it doesn't work. You can do tie downs. I've done numerous buildings just using tie downs. Unfortunately, the industry and structural has this wonderful cookie cutter that can give you the answer they need to how many of these tie downs or strap tie downs you can get. Well, ask them to figure out how many tension ties so that you have uninterrupted ability to put an exterior air barrier onto your building. Okay, concrete wall to wood framing air barrier connection? I don't think so. All right, so you look at the inside here, the XPS insulation with poly. Right there, that's what we're going to talk about. So I got a poly pre-strip. And so I use plate poly around the perimeter of a garage or basement or whatever it might be. And I do the perimeter and then I put a piece in the field. It's really hard to figure out rebates and everything and put all this poly in and make it nice, but it's easy to strip it and put it back on top. It is part of your air barrier system. So I'm going to pre-strip the poly, extend 1 inch below the finished concrete height. So I know where the concrete goes, so I can snap a line there. That's where the concrete is. I'll bring the poly up to 1 inch within that line. And there's a reason for that. And so I'm going to set the poly in the acoustic seal, and I'm going to put that 1 inch below onto the poly right there. Then I'm going to install high performance air seal tape onto the concrete foundation and terminate the height of the finished concrete pour. That's right here. So you already snapped the line, you know where it was. You put the tape there. All right. Before all of this takes place, you power wash the concrete into the gravel and do your work. This tape bonds. Now bring your best fingernail to the party, okay? You can't get it off. The best part is that when you pour the concrete, okay, you don't interfere with any of the air barrier because that's the height of the concrete. So here's the poly field sheet. That's right here. And that's taped to the pre-strip. That's the blue tape, okay? And so you can see the red line indicating the extent of the pre-strip. I taped the field onto it. So below grade assembly, I got poly with gypsum right here, typical inside condition. I got concrete slab poured to the height of the air seal tape. So you can see on the right-hand side, concrete's poured to the height of the air seal tape. So when you're toweling it, you're not cutting any air seal or connection to the concrete, but you're transferring that air barrier right through the concrete to the membrane or damp proofing that's on the outside and up the outside of the building, okay? So sometimes you got ICF. You can extend the poly onto the shoulder, and you can carry it through the concrete and up the front side of the waterproofing. That's one strategy you could do. All right. If you have the slab higher up and you can't go down the shoulder, because that's not really work, you can ring it up this way, put a salvagered vapor open on the foam on the inside so that water in the concrete can still dry out to the interior, okay? Or depending on what membrane you have to the exterior, okay, above grade. But you can make your air connection at the top of the ICF if you change the wood frame. So that was the below grade. I want to catch up with you on that there. I know we looked at that last time.
Great. We did have a couple questions come through there, James. Someone just asked for your thoughts on spray foam in unvented roof space.
Spray foam in unvented roof space. You mean on the underside of the sheathing, I trust. Okay.
Yeah, this question came through when, oh, sorry, go ahead.
I find that, well, for one, it's a highly risky assembly. I can tell you straight up that many jobs I've looked at, one thing you have to understand, roofs leak, okay? And if you have spray foam on the underside, you may not know this leaking. Best thing you can do is know your roof's leaking. And what I found on many projects is structural damage, because water is migrating into that upper framing and cords of your roof assembly. It could be joists, whatever, and rots. And you don't even know it because it doesn't make its way through. I have, even with open cell, I have been to projects in Golden and stuff like this, and all that kind of roof assembly. I drove my fist in there, and inside's full of water. I didn't know that until I went inside to see if there was water. And so inside that runs all the wood. So I find that when I'm designing or have to do a project, I put my thermal on the outside. I follow the cue given by nature. Okay, it just makes total sense both for the laws of physics and the fact that everything is highly visible. And then the structure itself, the thermal controls on the outside, the structure will survive roof leaks, etc. That's why it's okay if roof water comes through your light fixture, you know the roof's leaking. That's minor. Structural damage is a big ticket.
Great, thank you. And then there's a question in the chat that the folks did go ahead and answer, but I think just in case someone missed that or you're watching the recording, I think this is some useful information. Just if you would care to share the formula for the size of hole to cut in the EPDM gasket for smaller holes.
Okay, I can do that. So I use a couple of things. The first thing I use is common sense. And so let's say that I bought on Amazon, I bought a leather punch kit, okay, $20. And I got everything 1/8 all the way up to 3/4. All right. So if I'm doing 14-2 LV wires, whatever it might be, hose bibs, electrical conduits, all that fits within that kit. For example, if I have a 3/4 inch, I'd do a 3/8, okay, half the size. And so what that means is, as I go down the line to LV, when I get to the LV size, I look at the LV wire, I look at the end of my punches, and I try to pick something about half the size. And I punch it, and then I pop it through. It's highly airtight. You're gonna have to trust me on that one. But there is a simple formula as you move up when you get into ducts, HRVs, below grade, the rough ins for a basement, etc. As you move to, let's say, a typical vent at 4 inches, it's funny that all the aerosol caps are 2.5 inches in diameter. Primer, paint, peel stick, hairspray, I don't care what you pick, they're all 2.5 inches, okay? Well, if you take a EPDM gasket and trace a 2.5 inch for a 4 inch and cut that out, it's a perfect template. And you get a 3/4 inch return. By default, which if you're doing 3/4 strapping with no exterior insulation or whatever it might be, it fits perfectly. Once you reach the 4 inch line, everything above that, the gasket size is 1.5 inches smaller than the diameter of what you're going to seal. You got a 36 inch sump in the basement where you want to seal that, got a 34.5 inch hole in a rubber sheet, put it on top and tape it off. No problem. You got an 8 inch, 6.5, 6 inch, 4.5. There's not much to figure out. If I got a 3 inch, I'll do a 2 inch hole and I'll have a 1/2 inch return. So as you drop from 4 inch and you get down to 3 inch, 2 inch, 1 inch, once I get to 1 inch, I can do a 1/2 inch hole. If I got 1.5 inches, I'm going to drop it down. I'll do a 1-inch hole. You see, you can have a 1/4 inch each side returning, right? The difference out of that. And so the formula is really quite simple. When it's small wires, etc., look at this. A 14-2 wire shaped like letter 8, number 8. It's not round. And so I run electricals through a conduit, which is 3/4 with a 3/8, and I put intermittent putty in the wire hole chase, okay? That's a simple way to get that done. You can do a tape pinch type approach, many different ways.
Great, thanks. All right, those are all the questions we had in the chat, and I'll let you know, James, we are right on time, right on schedule.
Oh my God, I felt like an auctioneer. Okay. Everybody gets the slides too, so you can internalize them later. So there's a lot of content, and I want to get through it to give you that exposure, okay? And so I'm going to look at a roof to wall installation as built, okay? So what I'm going to do is going to take you over and we're going to look at that mock-up, all right, which is this one right here on the right-hand side. It's fully built, and I have that on camera right here. So I'm going to move on over there. Okay. This is the mock-up that you saw on that slide. Which is a vented roof assembly right here. With the rain screen wall assembly. It's got hardy cladding, 3/4 inch strapping, and 6 inches of mineral wool on the outside. Now, this is a 2x4 wall assembly. That's all you really need to build with. A 2x6 was a function of the old R16, not so much a function of what you need to build generally. And so with 6 inches on the outside, I've got an R24 continuous insulation on the outside, another 10 on the inside, an R34, throw a couple air films and components in there. It's easily an R35 wall assembly. This would satisfy most climate zones. And energy types. And it's really quite simple. A 2x4 wall, we know how to build them. 2 layers of mineral wool is quite simple to put on. I'm going to talk about that. And we're going to look at some of the air barrier strategies also. We're going to spin this around. We'll talk about it for a moment. Then I got some slides. Then I've got another mock-up here where the bottom half with the ceiling plane I have built, but I don't have the roof on it, so we can get a little bit more clarity taking place. You can see the insulation baffles and the rest of it in here. I'm going to take the insulation out. We get down to the ceiling plan. And what we're talking about is on the wall itself, I have an exterior air barrier. You can see right here. This exterior air barrier carries up and travels across the plates this way. This piece of membrane hanging down here, that's a water-resistant barrier. It's simply there for water, not air. The plane of the air transfer goes from the tie deck to the plate over to the polyethylene on the inside. Sorry, I have a problem here. Get rid of my phone, sorry. Okay, so I talked about the air barrier, but here's where it connects to the poly on the inside. As you can see, the tape came across and transfers here. What do you think? There's a piece of tape right here and then some wood. Well, wood is part of your air barrier. You can't blow it through a 2x4. You can't blow it through a 2x6, 2x10, 2x8, 2x nothing. So it can be used as part of your air barrier. If you seal the joints of the lumber, it can be part of your air barrier system. So what we've done is carried that across. And you can look on the inboard side, which I'm going to take you in. And we'll switch over to a little mobile camera. Gotta take you for a little ride here. So you can see on the inboard side that the air barrier comes across, okay, and transfers right here. There's acoustic seal. Right there. That's acoustic seal.
Well, that acoustic seal connects to that top plate. That top plate is connected to the tape on the outside. So the tie that comes up connects to the air seal tape receiver, transfers through the wood to the acoustic seal, which then connects to the ceiling poly. The interesting thing about the ceiling poly is I actually measure it. And so I know poly never gets measured, doesn't get a lot of attention on site. Usually just gets kicked around and stapled all to pieces. But it's actually a very important component to your air barrier. You think about, okay, I measure the room, I add 6 inches, and I measure and I staple it on the top plate and have it hang down to the bottom plate. I do my perimeter, and then the ceiling falls into place all by default. When I do that, it makes really interesting cones in the corner. And when I staple it, I only staple it to the top plate. I leave the bottom plate unstapled so I can lift it up and stick my acoustic seal underneath it and pat it back down so I don't get all mucky, right? And so you look at the other side, you can see where I don't have the tape on top. Now I'm just going to back you off a little bit here. Okay, and so when you do this way, you make these nice little cones right here. Okay, well, when you do the acoustic seal, you put it behind so I can lift up my flap, stick my nozzle. Well, I've sealed it in, but I can go underneath here. I can run my acoustic seal, pat it into it. I take the nozzle, put it inside the cone, and then I can staple it square in the corner. See, when you do this properly, you automatically get these little cones in the corner. And so you don't get this balled up poly and all of this areas where you're trying to make an air barrier transfer from the outside to the inside, and it's just a tinted mess. This is an organized install. This here wall poly that I've notched right here will go back onto the wall after it's stapled and done, like so. This is simply vapor control. It only needs to be lapped. That's it. This is air control, which takes you across your ceiling plan. Now, how do you get from one room to the next room, and how do you deal with a surface penetration? That's what I'm going to look at now. So I'm going to take and put back to the other camera. And we're going to look at the top side. Okay? So on the top side, you can see something that those that are familiar with this might go, what the heck is that? Well, I got the membrane on top of the plates. Out here. So what is this that I've done right here? Right here. Normally when you frame, you have this poly between the plates, right? And it gets done during the framing process, and it might be done nicely, it might not be done nicely, might be sticking out, hanging out, cut off, etc. But it's critical. It actually is the transfer of the air barrier from one room to the next room. And so it has to be connected. Well, how do you connect it at its intersection? When you got flaps going this way, you got a vertical transition poly going this way, and you got three-dimensional air control you got to manage at that pocket instant interface. Well, it doesn't get managed well. And so there's an easy way to work around that. We're good. And so I put the membranes on the top. And this here, what I have on top is basically a self-adhered poly. And so it's got texture and grip. You can ride on it, and even if you do damage or scrape your cords on it or roofing, because it's self-adhered, it's still airtight because it's glued. The wood bridge is airtight. So it becomes highly resilient. I have a service wall, and I got to put a service penetration wall. And so I can pull a hole. I put a EPDM gasket, which I sized for my pot. I tape it to my self-adhered poly because it's right here in my face. I got no hidden components or kind of sheet spray foam in. I mean, when the poly goes between the plates, you got to try to seal that poly in a hole. Well, it's all kind of silly. So put it on the top side. You can get exceptional air tightness. It's reviewable during the course of work. This is right in front of you. There's no hidden components. So once I coil a hole, I put the gasket on. The gasket goes down to the joint in the plates, and down to the joint in the plates. It gets taped to this. The acoustic seal carries right across the whole gasket 9 yards. Very simple, reviewable condition. I can get exceptional air tightness. I can put this in. I got the flaps coming up. If I just turn the pipe, I keep the flaps in the upward position. I'm done. It's like incredibly simple. So it's not taking you through this here, and I'm gonna take you over to a table that I have just over on this side, which has the lower half of this assembly that we can look at, okay? Okay, so this is the lower half of what I was talking about, which you can't see with all the trusses and everything on there. But now you can see what's happening. Here is the poly vapor control for the partition wall interface. This is the solid here membrane on top of the plate, which runs down through the joint between the top plate and bottom plate. You can see the acoustic seal that I've installed here because I put part of the ceiling poly on. You can see the little cones in the corner, little cone in the corner. Poly comes down to the bottom of the plate, okay? And it's stapled only in the top plate. So when I'm done, I'll run the blue tape across all the staples on the top so I don't have any holes in my air vent. And I was at the same time, the wall poly just simply comes up and laps onto it because it has nothing to do with the air control. It's only vapor control. This whole concept of taping the wall poly, not required. Okay, waste of tape, waste of time. So you look at the surface penetration. So I have this on top of here. Okay, we can have gussets here, here, across my pocket. I have a gussets going down right here. And I'll bring a camera over and you look at that. And so I'll get a surface penetration right here into my surface wall. I can install my service pipe. I take an EPDM gasket, okay? I have a 2-inch pipe. I cut an 1.25 hole. The way you install these things is just put your finger and lock it down in place and then just rotate it around. Now I'm on there. I can then staple it into place. On the printer. Pretty simple, so far. Now, this is going to make my air seal to my pipe. This is my air seal from room to room. You can see the acoustic seal is going to come right along this line. I take my tape, and to take tape off, just run your thumb on the tape side, okay? And it'll stick to your thumb. It's like so. If you try to take the release off the back side, okay, it becomes incredibly frustrating. It's hard to do. So just take it, stick to your thumb, take most of it off, run the tape around your gasket. Really quick and simple. And it's like, it doesn't take much of a skill set here. You don't have to worry about being all pretty and accurate. You're making an air seal. I cut my tape. My gasket is 8.5 inches wide because I'm 5.5 across the top, 1.5 on each side because I want to get to this joint. Okay, because that's where I'm sharing my transfer to my from room to room is at this joint right here. Okay, this joint right here, this acoustic seal. It's in the joint between the top and bottom plates. That's the only area shared because the air barrier on the outside, exterior air barrier connects to the top plate. The polyethylene transfers from the bottom of the top plate at the joint between that and the bottom plate. And so you can go from the top, over, down, and across and back along your ceiling plane. You go along, really quite simple. Put on last piece of tape. And I have now an air seal for my penetration Now, sometimes you say, well, when's this gonna happen? Well, anytime the mechanical works and puts that first pipe through, just slide a gasket on it, just leave it there. Leave the gasket up here, who cares? Come by anytime, slide it down and seal it. And then do your poly across the top. Okay, on the other side of the wall assembly. Canadian version. Here's my exterior building, comes up. Here's my receiver tape that connects my plywood to my plate. Okay, and so it's called tape to the tape. So I come up with my tie deck and I tape to the tape. Transfer sugar wood. All the joints in my top plate are sealed. This is one monolithic top plate all the way around. And so this air barrier connected these air barriers, no issue. When does this take place? Well, you wait for the truss. So I've done this with builders. And, I show up at 9:30, 11:30, we're having lunch and the entire home is air sealed with all the receivers. And so how's access right here? Well, I don't know, you might have an 8, 9 foot ceiling, whatever. You have an interior scaffolding. You're getting ready for your trusses, getting access to work on this. Basically, you'll be standing down inside the building like this, just working on this. It's like really quick and simple. You can do all of this work and then drop the trusses on it. Here's the interesting part. You can slide your trusses on it. You can think about it. It doesn't matter. It's still airtight. I can slide on it all day long. It's bonded to the wood, right? So it becomes almost foolproof. And visible. I have an uplift plate. You can see here. So my uplift plate is stopped in the wall. I simply put a larger piece of tape to cover the entire plate. So my air barrier transfers to the wood, transfers to here, can't leak behind the plate because the entire thing's sealed, okay, all the way around. I just carry the acoustic seal through. So what did I have to do that was difficult? I put a piece of tape. That's it. Now I can deal with these. So all of this is quite easy to deduce. And it's right in your face. Putting on a corner, you get a gusset right here. Okay, this is just a little corner cap. Not just cut it, fold it, simple. It's all here, really easy, nice stuff to work with. Okay, there's a couple of types. One here is called Sopra Seal Stick Flash Pro. Supreme also makes an air vapor barrier top membrane, which is great. Which is another type like so. This here's a 9-inch wall. It comes in 9-inch walls. If I have a 2x6 service wall, it's 5.5, 1.5 is 8.5. So my 9-inch wall makes to my joint between the plates by default. Much to do, just roll it on out down the center. Done. Any questions? I'm gonna move back. I'm gonna move back over to my straight ahead camera thing because I can move on from there. Okay.
Perfect. I'll let you get all set up there, and then we did have a couple of questions that came through.
I just gotta relocate my little camera and change, and I'm back.
Perfect. All right. This is just a comment on that first mock-up you're at, just about terminating a 3-inch plumbing vent open-ended into an attic.
Sorry.
She just said, James, please tell me you are not terminating a 3-inch plumbing vent open-ended into an attic.
Yeah, no, you see the roof's not, I didn't finish the roof either, so I would have done, it would have come through the roof, okay? Or
Okay,
whatever.
perfect.
This is a layered mock-up, just showing the layers, okay? And so James is going to tell you, no, I'm not terminating in the attic.
Perfect. Just some good clarification there.
Yeah.
Awesome. And then there's a bit of discussion about this in the chat. And so thanks folks for jumping in, but still wanted to pose the question to you, James, for your input. And I know that you did kind of touch on this a little bit as you were going through. Just so that we're all clear, why are you using tape over the top plate instead of the air barrier membrane wrapping over the top plate?
Okay, so the air barrier wrap is going to be vapor open. Could I use the air barrier wrap on the top plates? The short answer from a science perspective is yes, because wood itself is a humidity-based vapor control smart barrier, okay? However, the building code, building officials, those reviewing may give you a hard time because you didn't carry the poly or vapor control continuously across the top. And so I use the poly self-adhere just so I don't have to sit and explain all the different fundamentals of how this would work, even if it wasn't, okay? And so this is about avoiding issues on site. And it's no matter because I'd be using a self-adhered vapor open. I just use a self-adhered vapor closed. It's actually very supple and easy to work with and will bond to damp wood. So I'm okay with that.
Great, thanks. Those were the questions we had come through. And folks, Amanda put this in the chat in case you missed it. When James is up there with his mock-ups, if you select speaker view, you'll just see his screen. I'm going to be turning my camera off, so he's the only one on there. But if you're having trouble with that, it's the best way to navigate that. And James, I'll pass things back to you.
Okay, so I believe I left off on a PowerPoint, and it's about what I was talking about, okay? And so this is about getting a monolithic top plate, okay? Install the air seal tape, connect the plywood to the sheathing top plate, plywood sheathing to the top plate, gussets inside and outside corners. You can see that the top plate around the exterior becomes monolithic, okay? On the partition walls, the same thing, inside and outside corners, gussets, 4.5 inches long, cut a little V because I'm going to bend it over, so I don't need the corners, just unnecessary stress. I cut the corners off and bend it around. So you look at this here now, roof to wall interface. You can see now that the top plates, including the partition walls, are monolithic. Okay, that works out lovely. Interior top plate, transition, self-adhered, no problem. Extend it. It's self-adhered membrane right here down to the top plate joint. Okay, so like I said, 9-inch roll goes perfectly on 2x6 frame, and they make different widths of rolls or whatever. It just grab the one that works. Okay, provide an EPDM gasket. Okay, for the penetrations, simple. You look at that now and you say, okay, well, staple the perimeter and tape it just like I did live on the thing there. It takes but a moment. You can leave it on the pipe anytime. They can continue with the mechanical work. And if you don't have time to do the air seal work right now, you just come pull the gasket down later and tape it out. No big deal. Okay, you can do all your fire control for the underside, whatever. So you seal and perimeter that. Roof truss is installed. This is what you should see when you drive the site. Okay, and this is something I don't see very often. I see sometimes Tyvek flaps sticking out or all kinds of neat stuff sticking out. And theoretically that can work to transfer that air barrier across, but how do you fix it if it gets shear off? And I've seen this where the Tyvek is torn, discontinuous. The corners aren't sealed. They just come in two different direction lap, but they're not sealed. So if you run the receiver tape, there's nothing to tear off or shear, and you just tape to that tape. So that was the approach that I'm showing you. Okay, that's right there. That's an air barrier receiver. You can see here, depending on what your overhang framing is or whatever it might be, you put a water resistant barrier down. That disc just lapped. It's not taped. It's not part of the air barrier because the air barrier came up and across the ceiling plane. Everything above the ceiling plane, which might be in your heels, is simply a water barrier. Okay, doesn't need to be taped. Blocking installed to prevent venting into the roof space right here with the strap. So you got to vent your walls out, not into the roof. And perforated insect screen to provide to allow for well, obviously insect prevention and forward venting. So this I use, and what's shown here is perforated aluminum. It's a standard product you can get. You can get galvanized. You can get perforated aluminum. You can get perforated stainless, depending on what you're trying to do. Okay, it works really, really well, and it's simple break shape. Any machine, any roofing or sheet metal shop can break these pieces. Comes in a 4x10 sheet. Slit it, break it, good to go. I do it here in my shop. Air barrier transition to the top of the wall, tape to the tape approach. That's what I talked about. See, this one above on the heel, I cut it off so you can see the plywood. It's only lapped over. That's all it needs to be. Quite simple. So you start looking at this here. So here's a view to the underside as we start to build this roof to wall transition. We got the air barrier stuff done now. Now we're working on our thermal, okay, which is continuous up. So the wall carries right up through to the same height of the back. So you're thermally continuous across that transition, okay? You don't stop the wall at the plate and stop the bat here, so it's not continuous. No, the thermal plane must be continuous through the assembly. So view of the soffit channels right there shown. I didn't show the soffit, obviously you wouldn't be able to see anything. And then insulation baffles as required. I showed you that. Cladding installed. Here's the interesting part. So this baffle that's right here, this cladding stops 3/8 of an inch down, so this can vent out forward. So you get this neat little perforated line across the top of your wall. It looks nice. And it's highly effective for the venting, and you're sending out warm, humid air potentially because the walls get warm, the ground can be wet, and you send it out so it can temper before it goes back up and maybe enters into your roof space, reducing the chance for condensation, mold, etc. All right. So an optional approach you can do is you can put a baffle board on, you change your blocking, put a baffle board on, so you can hide the vent strip, and it would be something like this. Well, now you don't see it. I got a baffle board in front of it just by changing my blocking arrangement. So this is looking from the backside. No, I did not terminate the pipe in the roof space. Just to clarify that again. All right, this is just a layered assembly. And it's an attic installation and soffit baffle from the backside, just showing what's happening. And it's just an overall view of the split insulated wall and slope roof assembly. Here's what I talked about on the inside, okay? I notched a partition wall receiver right here. So you got that vertical one comes up and it comes right up. I just notch it down to the bottom of the top plate and just fold it out of the way. I'm running an air seal ring right there. I had nothing to do with it. That's vapor control. I just flop that back up later, okay? Air and vapor poly, like I measured the room. If I got a 10-foot room, I cut the poly 10'6". Yeah, I lay it out. I use a T-square, I cut it, and I put it around my perimeter, and the ceiling automatically falls into place. This idea of you got to go rib down the middle and make some kind of bass drum ends up with tented corners all the time that the drywallers managed to ruin. And that was actually your air barrier. So by default, when you have a vented attic. So set the perimeter square and true with the cones and everything else like that. And the drywall will have nothing but square corners to work with, and they'll provide an enhanced compression seal, and you'll get better airtime. Instead of cutting it, ramming the board in, or whatever magic takes place on site. Sitting on installed drywall, I know exactly what magic takes place on site. Okay. So install the air vapor barrier flush with the bottom of the plates. That's what I'm showing there. I showed you that, so that's why. Staple the ceiling poly into the top plate. Okay, so I staple it to the top plate so I can lift the flap up and put the pookie. That's acoustic seal out of the way. Put the pookie in there, and I can pat it down. And I don't have to get all over me. I got this protective shield. It's like wearing a face mask for that pookie stuff, okay, because it's nasty, right? And so when you get to a cone, okay, lift the flap, install joints. When you get to a cone, they're automatically formed in the corners. When you measure 3 inches down, if you just line it up at the bottom of the bottom plate, those cones will form. Okay, well, that was easy. And then what you do is I just insert the nozzle in there, shoot a little acoustic seal, take the nozzle out, push it square to the corner, pop a staple into it. And as I come along here, I install poly vapor barrier over the wall in a lap manner, okay? That's this here. I don't need tape seal. I don't need any taping on my wall. My air barrier is on the outside, okay? Extend to the joint between the top plates and staple to the bottom plate. So I bring it up to the joint. Everything goes to the joint, right? It's kind of fun. Bring the top ceiling down to here, okay? Acoustic seal transfers here. I bring the bottom up to the joint, and then I run air barrier tape over all the staples I put in the top, and it also holds my wall poly down. So all of a sudden, I have no fastener, nothing in my air barrier. Everything's concealed and airtight. Okay, so that's the roof to wall interface in a nutshell.
Perfect. We did have a couple questions come through, and you're doing great on time, James. This is wonderful.
Good.
All
good.
right. So someone asked, how would you seal an exterior wall beam pocket?
Sorry?
How would you seal an exterior wall beam pocket?
Exterior wall beam pocket.
Yes.
Okay, so at the air barrier there, you have two options. Believe it or not, you can make EPDM gaskets for square beams. Now, if you have a perimeter around it to put one on, okay? If you don't, you can simply use tapes. If you saw session 1, you saw the balcony program. You saw how I taped around a joist. You can imagine, would it matter if it was square, rectangle? It doesn't matter. So I can make a gasket out of EPDM for a beam if I have a place to put it. And the trick to doing that is just measure the beam size, shrink it, okay, by 1 inch all the way around so you get 1/2 inch returns, and trace it onto your EPDM. You then take your 1/8 leather punch or 1/8 drill bit and put a drill hole in each 4 corners so you get a slight radius to your corner. So when you cut it out, the rubber doesn't shear, okay? Then when you put it on, you'll get this 1/2 inch return. You can then, because it's a beam, you can run a piece of tape, and the beam's never coming out, it's permanent. You run a piece of high performance tape all the way around that beam to seal that rubber to the beam and to the wall, and it's highly airtight, okay? Or you can just use tape. I hope that answers it.
I think so. Thank you. And then any thoughts? So someone's just looking for your thoughts on the fact that some people like to nail the plywood from the trusses to the top plate to tie the trusses to the walls. So what are your thoughts on that?
To nail the trusses to the walls. Oh, I see,
Nail-
to extend the plywood up. Ah, yeah. And so there's no break in the plywood. Is that what I'm referring to? I trust. I'm going to answer that anyway, because I think that's the question, and it is a good one. Okay. And so I had a transfer, okay, of the plywood stopping at the double plates. Okay. It usually stops 1/2 inch down mathematically, whatever, at that general line. And if the question is such that may want to, for structural reasons or whatever it might be, to extend the plywood up to lock out the heel of the trusses itself, and that's okay. But when you do that, then you've got 2 choices. You can either run sealant on your top plate and set your plywood into that. All right, so now you've made that connection to the plate by the backside. It's a blind seal. Or you can use a 2-sided tape, which is a 2-sided butyl tape, which is highly effective. And you just again, it's tape. I have this 2-inch tape that I use. I run a piece of that along, and I set the plywood into it. Bang, done. And wherever I get a new joint of plywood, I put a little piece of tape and put the next joint up against it, so it's sealed. It's 3-dimensional air leakage, right? So it's gonna be sealed this way and this way. And so I do that. There are projects where I'll put the insulation on top of a roof and it's got overhangs. I can transfer the air barrier right through your overhangs to your plywood on the ceiling simply by doing that same backside tape approach. But that's another lecture for another time. I hope that answers.
Perfect. Yep. And you understood the question. So
Well, because
great.
it happens I get that one quite often.
Oh, okay. Okay. There we go. Just a question around how are you attaching the 6-inch mineral wool to the wall?
Okay, so when you're attaching mineral wool to a wall, I use what's called a temporary holder. It's called a wind devil. It's a plastic washer. Okay, I think I have one here. I can show you. Give me 1 second. I'll just run on over here. So this is called a wind devil. It's used to attach EIFS foam, exterior insulation finish system, you know, the stucco on foam type stuff. And you attach the foam to the wall holding that. It works well for the mineral wool. The other thing that I do is if I'm doing a mineral wool wall and I got 2 layers, I'll put a full 2-foot wide strip on the bottom and I'll hold them down with a couple of these. So just so you stay there now, okay? Then I'll start the second layer and I'll take a 1/2 sheet, because dimensionally I don't want any waste. So I'll start with a 1/2 sheet, and I'll do the same thing with wind devils with a longer screw. Okay. The rule of thumb when you're doing exterior insulated assemblies on a wall is it can be hard to hit the studs. And I have more of this in the slides. If you guys will get, you'll see some of this that I'm talking about for faster requirements. Okay. And so the rule of thumb that I use that works is I put 3/4 inch sheathing on my walls. So if I look at that and take a 2,400 square foot home, the upcharge that going from 1/2 inch to 3/4 is not a lot. When you compare to the fact that if I put, for example, 6 inches on the outside, and here's my fastener, I got to try to hit a 1.5 inch face on a stud. If I'm even 1 degree out on my direct hit to that fastener, I'm going to miss. Okay. So then I go to the inside and you realize, well, I didn't hit the studs, so I'm not structurally secure, but I penetrated through my air barrier. Let you go like, bummer. Well, now I can't take that fastener out. I got to go back and try again. That's not productive work. If I put 3/4 sheathing on, what I do is then I don't need to hit a stud. That becomes the structural backup. Okay. And so when I'm doing this kind of work, I'll do the first sheet, the half sheet, right, with the temporary holds. And then I'll do my strapping layout. And I do a Sharpie line X, line X, line X, just like a framing layout, right on the insulation. And then I'll take my straps, which are pre-drilled at the spacing depending on my cladding load, and they are pre-drilled and countersink. Usually a number 12 countersink bit works lovely. Sometimes a 14, depending if you go to a slightly fast, larger, faster. No big deal. But the straps come preloaded with the fasteners. So my helper, okay, zipper, I call him because he zips up the walls behind me, okay, is he puts screws into there. And when I'm handed a strap, it's got screws in all the holes ready to go. So I put it on that first starter rows that I put on, and I put one screw in it, and I got this 8-foot strap. And I go to the next one, and I got, so all of a sudden I got this row and a half of insulation on the bottom, and I got all these strappings standing there. So now I'm a bloody octopus, okay? I got arms all over the place. I just start stuffing it in behind the straps, pack it together, and zipping them up. That's how it gets done. And I do the same for roof assemblies. And let's put it this way, you can't bring it as fast as I can put on. Can't do it once you get the starter going. And when I get into the window, I show you how to make insulation starters. All the penetrations already have their insulation around them. So it's just a field infill. It's incredibly fast once you organize a process. And that's part of the problem as we move to this new world of energy efficiency is developing process, because we're still stuck in the process of the past, which is fundamentally doesn't apply to the laws of physics. So we have to turn the boat a little bit here. Okay.
Perfect. All right. Just a follow-up question there, and then we have a couple more, and we'll keep moving. Can you elaborate on the 3/4 sheathing that works and that works for air barrier and vapor barrier?
Okay, so here's the deal. You don't need to do the sheathing as your air barrier. You can if you like. Okay, you can tape all the joints, but then everything that you do has to transfer to the framing. That means around your windows, you got to tape all your rough openings and everything in that, because you got to caulk to your rough opening because you've connected to the sheathing. The sheathing, put it on and use it as structural attachment only. Put your water resistant and air barrier onto the sheathing, into your rough openings to the full extent, rod and caulk between your windows, which is the next one I'm going to show you, by the way, as we get into this here. Okay.
Okay, perfect. So maybe we'll get going with the other couple questions, because we might answer Jen's question in more detail as we move on. All right. Is the vent strip at the top of the cladding assembly to temporarily temper the air before it goes back into the roof assembly actually necessary? Have you opened roofs and noticed issues to go through the extra work to do this? What is this based on?
100% I've seen the issues. Okay. The whole idea is this: you got solar air temperatures. Okay. That siding, okay, you got a hot day, you put your hand on the siding, it's like, yeah, it's probably not cool. That's hot. Well, you got ground moisture. So you got hot air rising, pulling in moisture. You can have high humidities and high temperatures within that vented space. Your sheathing up on your roof, okay, can be cold. The air that goes into there, especially if you start thinking about night sky, and it takes a while for everything to warm up there. But the point is this: if I have it directly go onto the underside of my roof, I can end up with fungal and or deterioration, and I have seen both. Okay, as simple as that. And so the best practice for the intent of this webinar is to vent the walls independently and to have it temper, okay, with the other air before it goes back in. It's a buffering event.
Great. And then this is kind of a related comment, but he just said, James, it looks like you are really promoting a hot roof, as I see these vented roof details as a bit fussy and prone to damage during construction. So any comment there?
No, this is just a standard vented roof. Myself, I put the insulation on top of the roof. Okay, and that's another webinar. I don't do vented attics. Okay, I work with builders and we put the insulation on the top side. No more poly on the inside, all this kind of stuff like that. That becomes a rain screen roof. That's right, a rain screen roof. There is no fit. You could actually have your shingles blow off and you still wouldn't leak. Okay, so this is, I've taken this mock-up, I've taken it halfway to the right path. Okay, where I've shown you how to transfer the controls, air, thermal, etc., through a standard roof assembly. But as I move forward, and I'm working with builders regular, is we're putting the insulation on the top side. Okay. Even in passive homes, I'm a passive house tradesperson, all stuff like that. But even in high performance homes, the last builder I worked with, he transferred his air barrier through his overhangs. He put his insulation on top, and his blower door was 0.6. And he was just like he was a first timer. Okay? All he was given was a little bit of direction. And he basically slayed the dragon. He's like, man, it's amazing. And so he's got this wonderful rain screen roof. No issue. I don't put spray foam on the underside of roofs or decks. That's bad planning. Okay. That's a future issue. Fundamentally, by the laws of physics and science, will it work? Yes. By the laws of humanity? No, because roofs and decks leak, and you'll never see that they leak, and you can end up with some significant issues at that point. Okay.
Okay, great. We're gonna carry on. We have just about enough time left for this last section. We have about 45 minutes, so we'll move on to windows.
All right. Well, you're looking at high performance window installation. I'm going to take you through this quickly. There's a lot of components for it. I actually have one here that I use for carpentry student training that I'd be happy to take apart in reverse order so you can see it happen. But I'm going to run you through the front direction. If we have time, so be it. I want you to look at this picture for a moment. What do you find is strange? Well, I find not really strange, but exciting that the entire window is complete, yet the wall isn't even started. So I'm able to diversify my crews. I can go around and do all the windows ahead of time. I can plug in the field installation with a production crew. So I start to split up the work a little bit here and stop making one thing reliant on another. You see the sill flashing and the jams and all the rest, neatly notched and all the rest. Where's the end dams? They're in there, but they're hidden. And I'll show you how all that takes place here, step by step, in a high-speed manner, I suppose. Anyway, this is the way that I do an exterior air barrier for a window. Okay, I start the sill membrane 7 inches up so I can lap it over. I see so many times on site that the sill membrane runs right past the jam. It's kind of silly because the windows will drain at the corners. So I keep the jam membrane up from the corners, not to interrupt. More to be revealed. I'm using a aluminum angle. This is a high performance clip window with an aluminum sill angle attachment. I'm showing you tomorrow today. Okay. And so this is the peel and stick primer around there for 2 inches around there. Then you got to make a pocket because you got to think about, I got to seal this corner. It's got an XYZ axis with a piece of membrane. How do you do that without making any cuts? That's called a pocket. And that's what a pocket is. So I got a pocket left and a pocket right. And how do you make those things? Well, it's 4 inches wide because the minimum lap's 2 inches. So I cut a 4x4 by the length of my roll for my detail. In this case, 6.5 inch, depending where your angle. The angle counts for 2. I put a 2.5 inch recessed and 2 inches over with 6.5. Depending on your project, you got to figure what's width of roll do I need to make this work. Okay. You want to minimize the amount of peel stick on the wrong side of your wall assembly. So 2 inches is the minimum requirement. To make a pocket, cut out the release in the backside and fold it into a pocket. How does that actually take place? What I can do is I could go to the table, right? And then I'm going to walk up to that table there and try to show you, okay? How did I get in 2 places at one time? That's weird. Okay, so I put the X, that's my left pocket, and I take the Olfa knife, and I got to cut that release and remove it without cutting the membrane. So I take the knife and I flip it upside down, and I do what's called scoring. This is a standard technique that roofers use all the time for self-adhered membranes or self-adhered roofing plies, etc. And you score the backside of the release paper. All right, super. Put the knife away so you don't stab yourself. Okay, and then just take the release paper off the backside. Okay, and you won't cut through the membrane. If you do cut through the membrane, you need to chill out. Okay, because you're using the back of the knife. Okay, like holy doodle. All right, now fold it together like so, and press it down. Use your paddle. This is an easy tuck paddle, best peel stick tool ever. Excuse me. And I paddle it down and make what's called a dog ear. Okay. And so now I got to take the dog ear and I got to make it inside out. So put my thumb at the bottom of the ear and flip it inside out. And so now I've got an X, a Y, and a Z axis with no cuts in the membrane. So there's 100% watertight. It's going to be 100% airtight. And the dog ear goes against the jam side. So there's an expression I use called dog licks the jam. You can make toast and check it out yourself, okay? So the dog licks the jam, okay? There you go. And so now you got a pocket that will fit in that inside corner. Here's the pocket. One of the things you need to understand for an exterior air barrier approach on a window install, all the cuts are vertical, full stop. All the cuts are vertical. That's it. What direction? Vertical. So the yellow lines, I make a little vertical cut here, wrapping around the angle, little vertical cut here, and extend it across. There's my X, Y, and Z axes. All right. And here's the ongoing pocket. So I look at this here, so how do you get this X, Y, and Z planes into place? It's a hot sunny day. You know there's primer there. If I take all the release off, it's just not going to work. I'm going to be frustrated. So you take one plane off at a time. So I want to set the Y-axis first, and I put the dog ear on the jam. Dog licks the jam. So here's my Y-axis. So I just score a little 1/4 inch beyond in a happy face. You're always happy. Okay. And then I take this release off. I set that into the corner. I set the axes, and then I put it on the wall. If you seat the axes, the wall always falls into place. I then reach behind, take the release, come and tuck it under plane number 3 here and stop. I expose the X-axis. I use my cool paddle. I set the axes and I put it on the wall. And then I take this tail and I just pull it out. And I set planes 3 and 4. I use the paddle to pinch seal the edges. You see peel stick peels up. Not enough attention is given. It's pressure sensitive. Okay. So I just pinch the edge of it with the paddle. You can't get it off. It's amazing. Now you start with the gussets. Okay. The gussets are how you seal that pinhole right here. Okay. Because I wrapped the jam, but it's still got a pinhole right here. I need to run some membrane around it. So where do I get the gussets from? Well, I get it from the jam piece. So the Tyvek went 7 inches up, and the membrane lap is 2 inches. So all the jams are 9 inches long. All the pockets are 4 inches wide. All the jams are 9 inches long. You can pre-make all of your papers if you know the rough opening of the window. You don't have to do this on site. I've done this for builders numerous times. Give me your rough opening cut list, and I can bring you the entire thing wrapped in a bundle, one for each window, and you install it. And all of a sudden, you don't have to know how to do it. But if all the pieces are pre-cut for you, then you get osmotic learning. You just install it by the cut size, and you see with your hands how to do it. All of a sudden, anybody, and I've done this with secretaries, it doesn't matter if you're even in the trade. They come to workshops. We have team building events. Some firms, they find this fun, so I entertain them for a day. And I have the receptionists and that doing better jobs than some of the construction managers. And it's just funny, but it's so simple. And they all learn it, and you never look at a window the same. So if I have a 9-inch pocket and a 2-inch flat, I'm going to cut out a piece 4x2 right here. I'm then going to cut an inch off. I'm going to make a little 3x2. That's my gusset. So my gusset is the cutout from the jam. There's no waste. And then here's the cutout for the gusset. It's really quite simple, but this is the pinhole, and I want an inch in each direction of the pinhole. 1, 2, 3 directions here, so I can mold around. I cut the corners off. I get rid of the other corners. I don't need the corners. Okay, they're just getting away. And so then I install this here, and I place it into there, and I project it out about an inch. Don't interfere with the dog ear in the corner. Do this side first. Set your axes. Do these inside first. And then take your thumb and just roll it back and forth, and you can mold it like that. Then I pinch seal it. Here's it with install. I then take the jam that I took the gusset from, and I put the angle in. I know that my angle is 2.5 inches back, so I can measure from here, which is this corner here. I measure back 2.5. It's 1.25 inches high, and I cut out a 1/8 notch for the angle. Simple. Once I pull that out, I can dry fit that notch onto the angle. I take the release from the top, take it down a couple inches, set this plane, pull the release off, lightly press it into place, roll around the corner, and push this side down. Once it's placed, then I rub it. Okay, you can see the dog ear in the background here. You can see the gusset. That's peel and stuck. Everything you put peel and stick on, what you put it on should transpose through. Otherwise, you've done peel and float. There's not supposed to be peel and float, it's peel and stuck. So now that I got this on, I get the sill membrane on. So I'll take the sill membrane, I'll dry fit into place. So right here, it's dry fit. I got the release still on. The sill's all primed. You see that? All the laps of the peel stick are primed, but the release is still on. I dry fit it with my paddle. I then lift up the front and tuck the release paper under the sill. Then I take the front, fold it down, and seat it off. Now that I've got the front done, I pull it back and take the release off, and then just roll it into place with my paddle, one plane at a time. And I end up with a perfect install. You can see my laps. You see everything transposed through. The sill's done. This is the jam membrane. It's going to come up 4 inches past the head, and everything extends 11 3/4. The reason that this is happening, okay, and you think about that is, I buy Tyvek or whatever I might buy, whether it's a 3-foot roll or a 9-foot roll or whatever, but I cut 18-inch, and if I'm doing exterior insulation, I cut 24-inch, and I call it a starter. In this case here, okay, I'm extending back 11 3/4, okay, on each side. I have a 2x6 wall with 3/4 shear. That's 6 1/4. 6 1/4 plus 11 1/4 makes 18. So I know that my membrane, if I go to the full extent of the framing, will come out 11 3/4. I can mark that. So when I'm done, I have a picture frame and a purposeful install. Does that matter? Yeah. I have worked on projects side by side, same builder, except one was for my colleague. He asked me to do all the strip in. I did. Everything was neat, tidy, and organized. And the house next door, Don Byler's, looked like it was done in a windstorm. And people will walk by and say, why does that house look so much better than that house? Well, that's a wonderful opportunity for building to explain, well, the reason it looks so much better and looks organized is because, well, we actually have a plan. We do it for exterior air barrier, and you have this wonderful chance to express yourselves. And that's exactly what we did. So you can see here, the jamb extends 4 inches past. All the cuts are vertical. Yep, vertical cut, and it flaps underneath. So it laps over here 4 inches, and it goes up here 4 inches. So for every window on exterior air barrier strip in, the length of the jamb paper is the rough opening plus 1 inch. That's it. I have 48 inches high window, 49-inch jamb paper. 24-inch window, 25-inch jamb paper. None of this, it's about having a plan and a process. How about the sill and head? It'll be the rough opening plus 11 3/4 times 2, because that's how much it extends on each side. So all I need is the rough opening. I'll tell you whatever you need to know. The pockets, the gussets, the jambs, the papers, all around with elastic band, plunked in front of the window. Go. All the cuts are vertical. Do the head. Head extends up, same 11 3/4, okay? All the cuts are vertical, wraps to the underside. Now you have a water-resistant barrier. All things are lapped, shingled, super. All right, now I'm going to tape all the laps to make it a water-resistant barrier and an air barrier. So I started that and I worked my way up from the bottom, just good habit. And I come across here and I got a lap, and I got a joint right here at the inside corner. Well, I put a piece of tape there and I extend that tape out 1 inch and I roll it around as a tape gusset at this corner and this corner. But that will be a wrinkled tape gusset under stress. So I take what's called a retention strip right here, and I put it over top of that gusset at the midpoint. I make a little slit right here, and I fold it around, and I wrap that corner. So you can see here, you got a nice tight double wrap corner, air barrier, good to go. And here's what it should look like finished. Every window will look exactly like that on the entire project, and every single piece here can be pre-made if you know the rough opening. That's efficiency. Now you get into this. Well, hang on a minute. Whoa, what are you doing? No, I'm going to put the insulation on. What about the window? I can do that later. Oh yeah, it's got no flanges. Oh, life is good. Okay, so we get down to this stage here, okay, to say, well, I got plywood on the top. Well, I'm putting 2 inches on this here exercise for the carpentry students, okay? And so the head has got 1.5 inches plus half-inch plywood to make 2 inches. The reason I got plywood at the head is that's where I'm going to attach my flashings, etc. And I'm going to do short screws up there. The plywood's done with long screws into the air barrier to pressure seal. You can see a different type of retention plate. Here I used a metal insulation plate. It's a roofing type plate. That's what I had. Don't really matter. Typically I use the aluminum ones. Unless I'm doing a fire rated wall assembly, then I use the metal ones. So you start to look at here. This mineral wool itself is hydrophobic. Okay. I think everybody should know that. Let's see if I can express that for you, which I will do with this piece of mineral wool right here.
I'm just going to stop your sharing there, James, so folks can see what you're doing.
You can see the water like ball bearings on here. Everybody see that?
Mm-hmm.
Right, so it's a water resistant barrier. It's not recognized by the building code as your first and second plane of protection. It's actually your third plane of protection, or arguably it is the second plane and the Tyvek is the third plane. But because of that, my plywood receiver that I put at the head, I put membrane on it and I lapped it over the mineral wool so water will drain down the mineral wool. That's all that was about. I get to the sill.
James, sorry, you just have to share your screen again.
Oh, I'll share my screen again. Share.
Yeah.
Okay. Thank you, Jenna. Okay, so
No problem.
you can see I
Perfect.
put the Tyvek over top of the head receiver for the flashings, and it laps past the mineral joint. The joint's right here. This is a water resistant barrier. Water will run straight down at this point. So I go to the sill. I have a waterproof membrane on the sill as required. It's my air and water barrier, but I got insulation on here. And so any water that comes here, I don't want to drain it behind my insulation. I want to drain it forward of my insulation. How do I do that? Well, I use that same membrane flashing tape I used on the top plates for the other mock-up, and I cut it to suit. Well, this happens to be 4.5 and this is 9. It kind of worked out pretty good, right? And so I prime this And the reason you prime the mineral wool, it becomes crunchy like my grandma's hair used to be as a kid. She used to give me a hug, and I was always amazed by her crunchy hair. And it does the same thing to the mineral wool with the primer. It becomes a crunchy receiving surface for that membrane. So I score this here membrane in the center line here, and I mark the center line here so that when I go to install this, I can line up my center lines, I can fold it back, and I can do one side at a time and do the other side. And now I've got a pan that directs water out of the insulation, and it is simply a water resistant barrier, nothing to do with my air barrier, okay? I start to look at this here, so let me see, what have I done? I've put in an air barrier and water resistant barrier starter onto the sheathing, and then I put an insulation starter on top of that, and I still haven't done the window. And let me see, if I know the rough opening, can I cut the insulation starters just like I did with the paper? Short answer, abso-freaking-lutely. Of course I can. The sill is equal to the rough opening, okay? The head is equal to the rough opening plus 16, because each of my starters here are 8 inches. I put a 10-degree slope on the top here and a 10-degree slope at the sill here. So I can rip all these at shop. I can buck them into length. I can bundle them and call it by window tile. You're ready to go. That's pretty efficient. So let's look at a flangeless window. Now, you want to make sure you get the windows in the right orientation. I've seen upside down windows, backwards windows, all kinds of stuff, but they got weep holes, okay? So put the weep hole to the outside on the bottom. But sometimes they got a hole here. It's a hole to equalize the pressure in the frame, okay? And don't put that on the bottom because we can like direct entry for water, right? Kind of straightforward. The interesting thing about the clips going on, many of these clips are designed to clip into a chase. They'll have rounded edges, and you want to put the rounded edges against the frame and rotate it in, because if you put the square sharp edges in, you're going to puncture the frame. So here's an insulation clip, okay? On myself, I use my shim stacks, horseshoe shims. I take tuck tape, I cut it in half, 1 inch wide, and I wrap each stack, put a daub of sealant, put it in the corners. Helps me stay there because these windows are heavy, and I don't want these things misbehaving. I want them to stay still. So I'll drop the window into place. Once I got the window into place, you can see the clips holding the window in place from the back side here. And when I put this in here, you can see this sealant along the top of the angle. That's the air seal for the window to the aluminum angle. I've also put sealant on the top of this membrane, and along the joint of that membrane here. Why? Because I had a caulking gun in my hand. Do I have to? No. But this is about best practice, okay? And I have a gun in my hand, and it doesn't have to be pretty, okay? I'm just locking everything down, okay? So now you can see I'm ready to install the window. I put it on the shims. I push it in, you get the sealant bleed out here, and you go, well, that's like a mess. Well, fortunately, there's cool tooling sticks shaped very much with a chisel end, almost like a 1/2-inch chisel. And you turn it and you do like a grater, and you run it along, and it cleans it right off, clean as a whistle. And then you go the other side, clean it right off, clean as a whistle. And so do it when it's wet. Any residual that's left behind will rub off during the construction clean at the end, okay? So there's no excuse. Here's a very, 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 super very, largely very, many varies important point that gets missed all the time. And then when I'm doing field testing on site or rainwater testing or air leakage testing is these clips. See, you need to seal behind the clip as well as over the clip to make a transition from the paper to the window, okay? Well, what happens is the sealant just on one side, you get blow by past the clip at the shoulders, okay? So what you need to do is when I put a window in, I put it in with one fastener with the clips, so I set it into place. And then I loosen off a fastener and I install sealant behind and I put the fastener back in. So this is a black line I do here. This is line of air seal. That's where the air seal is going between the window and the wall. So I'll do that line of air seal. And so I said, make sure my sealant is in the line of the air seal, right? And so now I know when I put my backer rod and caulk, so you see all the clips have been air sealed all the way around. Takes but a moment. You know, like it's not half pretty, okay? I clean it with a tooling stick because when I put the backer rod, then you end up looking like you had a fight with an ice cream cone. So if you just clean it up a little bit, it just makes it easier. But the backer rod goes in between the clips. Some clips will allow for the backer rod, depending on the window manufacturer. These ones don't. They actually provide backing for the sealant by default. So the backer rod goes between the clips. And I set the backer rod 1/4 to 3/8 deep. I need a 1/4 inch profile at center for a proper sealant profile, okay? And so that's pretty simple. My bottom is clean. All this is done, backer rod's in. I didn't install the sealant for this example. because I need to take it apart at some time, right? And so that would be nasty, but put sealant, which will connect from the sill angle seal here, up to that seal, all the way around, back over to here. That's the line of the air seal. For fenestration, windows and doors, the air seal goes in the inside, full stop. None of this outside madness and all the rest of this talking, okay? That's not where it goes. Again, you can see, now I'm gonna start putting straps on, okay? And so I set my straps here. I got a 4.5 inch line. Without getting into the nitty gritty of it, I've set where this line across the top here is where my head flashing will go. And the back leg of my head flashing will terminate at the top of my plywood receiver to receive membrane, okay? So I'm putting all my straps on and they all line up at the same height because that's where the head flash is gonna go. So once you establish that, it's quite simple, okay? Now, I have my inner jam flashing stops a 1/2 inch from here, so I get drainage right here. You can see in my sill straps, I have a drainage at this corner and I have drainage at this corner. That's where water comes out of windows, okay? Doesn't come out everywhere else. It just comes out in the corners. So let them be free draining. But I also have a window, which is my thermal component, and a wall, which has got insulation on it. It's also got insulation inside the wall, but I got a gap around it for the rough opening. So how do I make it thermally continuous? Well, I use what I call banana bread, okay? And when I say banana bread, I mean, I take mineral wool back and I slice it and it falls over and it kind of looks like banana bread. I think so. And then, so I'll take that, about a 1.5 inch wide and about 5/8 thick, and I'll stuff it between the window. The reason I do that is, the reason the rough openings there is so that you have some ability for movement and not transfer the forces to the window. Well, if you take a 5/8 slat of mineral back and push on it, it's super soft. Yet I stuff it into that opening, the window can still rack and I'm thermally continuous. And I leave a gap between the rod and caulk on the inside and the banana bread on the outside. So I have a drainage path and it comes out the corners because it never is tight fitting to the corner and mineral wool is free draining. So the interesting part is doing this system here. I water test these and I have in the past to 9,000 pascals, simulating 441 kilometer type winds and stuff like that. And I test them through a rain rack test and I never get a drop of water on a sill. And you think, why? Well, because we can't get past banana bread. It's like, wow. So I get thermal continuity and increased water penetration resistance. Nice. And so I'm looking at this here. You can see banana bread has been stuffed in its place, all 4 sides. Now I'm going to look at this here and say, here's my strap, and I'm going to have return trim to my window. I'm using 3/4 stock or 3/4 or one by stock. So I'm going to attach to the side of this strap, and it's going to encroach on the window. So once I know that encroachment, I'm going to set my sill board so I have the same amount of encroachment onto the frame all the way around the window. How do I change this window in the future? Take it out for the inside, put it back in. I never have to take off my trim, my cladding, nothing. I go outside, I cut the sealant between the trim and the window, and I take it out for the inside and I put it back in, go back outside and caulk it again. The trim stays, everything stays, and I don't muck with any of my major controls, okay? But once I got this height set up and my encroachment determined, I'm going to take my sill flashing. Well, I'll put my board on because I know where the height now. And that's my data starting point for my trims. I know all my trims now will stem from this point. Oh, excellent. So I put my sill flashing on here with end dams, which I make 1.5 inches high. Okay. And that's what they look like here. So I fold them up and then I fold it back on itself. Okay. So that I have an angle that will sleeve behind. You see how the trim board will slide down on the strapping, and I back cut it so that it'll go over top of the end dam and you never see it. So it looks neat and tidy because I put a kerf in the backside. Okay. Just see a picture of the end dam and all the rest of it. And you can see now the sill flash is installed. There's the weep hole for the window, and I've got a starting point. So now I'm going to look at, I'm going to put my trims, return trims get attached to the side of the straps. Okay, right here. Here's my board, my trim board notching around here. So I have a 1/8 offset right here. So I've notched this out 1 inch of my jam coming down. And then on the back side, you see the saw cut? Just like that, see? And so when I do that, that little saw cut sleeves into that little end dam, and you don't have this, looks like somebody beat it with a beaver, okay? It looks neat and tidy, okay? I've seen some ugly sill jam interface. It should look neat and tidy and follow the angle of your sill. 10 degrees, set it at 10 degrees, good to go. So you start to look at that there. Here's all the wood trim installed around the window. And I knew that worked because if I'm going to set this height and I got this data point height here, I know that my head is going to be 1/8 lower than this here. So I can measure from here to here. I know the jam size. I know everything. And I can give you all of these wood pieces from home from the rough opening. All of it stems from the only known data point, the rough opening. If you sit and internalize something to this level, you can pre-cut all this. All the trims have a 3/4 by 3/4 dado or whatever I need to suit a baffle joint for my cladding. So my cladding will tuck in behind it, neat and tidy. And so now I'm going to make the head flashing. So I just drew this here, make a 1-inch end dam, put a safety edge on here, fold it up. Now you have an end dam. Really simple to do. Place that on top of the plywood receiver and it gets fastened there. Pretty simple. So the previous line from the rough opening was 4.5. That's where that flashing goes. But I got to put a membrane on top of here. You see the primer again, just like the sill. Well, I take this here and I could score this membrane and I could do whatever I like. So this 2 inches here is going to go on the tie deck. This 2 inches here is going to go on the top of the mirror wall. And this 1 inch here is going to go over the flashing back leg. But I'm not going to remove this release paper. I'm going to leave this one on and it's going to lap over my flashing because it's only a water resistant barrier. I don't need to stick it to flashing. So if I ever want to change my flashing, I can just take it, lift it off, put a new one on and fold it back over again. If I have time, I got one behind me. I'll take it apart and show you. So you're installing this tape. It's the same idea. One plane at a time. You see it go along. Press it all in there with your paddle lightly. This is a supple membrane. First you seat it, then you beat it, okay? So seat it nicely, okay? And then you can rub it into place, okay? And so now you see that this is getting set up. I dropped the flashing on there. I carried my water resistant barrier and air barrier from the wall, and I lapped it over top, so everything's shingled. So I'm shingled at the insulation layer. I'm shingled at the back layer. Now I might have a windy site. This is my stinger. And what it is basically a hammer tacker that shoots out 1-inch staple, cap staples. And I just whack that into place. So if I don't want the thing to blow away, if I got that kind of site or that type of year, it's a shoulder season and it's windy, I don't have to worry about it because these type of staples will still keep it airtight. You just don't staple in the field, the standard staple, when you're doing exterior air barrier. Only staple where you're going to lap and tape, okay? So now I put the insulation on, so I'd be carrying off the wall. I just put a strip because I ran out of mock-up, but I'd be carrying up the wall, okay? And I'm just showing a countersink bit here and the little strap that I'm going to put above there, a 5-inch strap in this case. I just pre-drill the countersink so that the fasteners go right into there. This here, I've given you a link. You go to this link and you can go to the local energy efficiency partnerships. We wrote all this literature for them. This shows you the various weights of typical type claddings. Stucco, stucco is 10 to 12 pounds a square foot. That's like a little bag of sugar, right? You're like, oh, is that all? Well, it's not crazy, right? So this whole exterior insulation thing is not a problem whatsoever. Here's some suggested lightweight, medium, heavy, fastener strapping. This is when you go into the studs. You see on the graphic, right? That can be very challenging to do. Okay. There's also, if you download this guide or go look at it, it'll give you some notes so that you can do the same thing with 3/4 sheathing. So I look at it this way. If I have 4-inch insulation, I use 6-inch fasteners with 3/4 straps. 2-inch, I use 4-inch fasteners, okay? So my fasteners are always 2 inches longer than my insulation. There's nothing to think about because it goes through the 3/4 strap, through, for example, 4 inches of insulation, then 3/4 sheathing. I'm already at 5.5. So the maximum I can penetrate into my wall cavity is a 1/2 inch, which works for missing electricals, all the other type of lights, which should not be there, and you're allowed that, okay? You can look here. That's what we had for roof to wall. We got air seal on top of the plates. Here we got the full window done. The wall's not done. Vented roof, flanges window, Yahoo discussion. Now,
Perfect.
Here we have time.
We have a couple questions, so why don't we spend some time answering questions and then we'll use our remaining time to look at the mock-up.
I'll take it apart
That
if you
works.
want to see it, take it apart. So that's all.
Sure. So the questions we had come through here, and folks, if you have other questions, feel free to pop them in the chat. Someone just noted, I have seen a large number of builders do negative laps for their flashing and rely on high performance tape. So the building/roofing wrap being on the back side of the flashings.
Yeah.
And they understand that this is a direct violation of code. Are they missing anything, or is this an acceptable practice?
Okay, so I'll give you the straight answer, okay? It's kind of how I'm wired. It doesn't comply with the building code, but I can tell you categorically that if you exterior insulate your wall assemblies, I tested them for years with class after class after class with students and people that first timers, okay? And I test them to, again, 9,000 pascals, 441 kilometer-hour winds. and with a rain rack, a 1105 standard on steroids, okay? And in all the years I've ever done a test, I've yet to ever see a drop of water on the Tyvek, ever, okay? Now, I do training with building officials also, and I have this discussion with them, and they just keep reverting back to the notes section of part 9 that shows you a little 50 millimeter lap over the back leg of the flashing, okay? Well, first off, the flashing is not at that plane anymore. It's out on the insulation. And so that membrane that goes through, because it's not metal anymore, it's a membrane, no water can ever get there. And if it did get there, you've already got a continuous water and air barrier plane all the way down the assembly. And so it becomes a little bit, well, unnecessary. So what I find most unnecessary is a waste of time discussing it with an official that who might be inspecting is just plan to lap it, okay? But technically, no big deal, okay?
Perfect, thank you. The next question is around your dog ear method. Is there a reason you'd favor this method over using flexible sill flashing?
Yeah, because you end up with tented corners. Installers will puncture your membrane. And what I found, because I've used them, of course, and a lot of the passive house techniques, ExoSeal and all this kind of stuff. I come back later, and when you stretch something and you put it under stress, it really wants to come back over time. It's kind of the nature of things, right? And so, can you use a flexible membrane? Sure, you can. When you got a back angle, though, it's going to be a bugger, okay? And one of the things, too, when you stretch your membrane, you might start at 40 millimeters thickness, but by the time you stretch it around, you're down to 20 millimeters. Where is the damage going to take place during a window install? At the corners. So I do this technique because a lot of the skills I've shown are transferable. It teaches you how to make all kinds of seals at corners, the origami necessary. That's how a dog ear and a PVC membrane. It's the same thing they do, okay? And so it's about giving the base skill set, all right? Now, things like flex wrap by Tyvek and stuff, the flexible wrinkle wrap, but you can't make an air seal out of that effectively, okay? And if you got an angle, you still got the same problem. So that's the reason that I go with the dog ear approach for a couple of reasons that I can pre-make the dog ears at home. All I need to know is how deep I'm going to put my sill angle, and I can make every single piece completely ready. And then, when you go to site, it says, I'm happy to, I'd be happy to race somebody and see how fast you get your window done. I mean, the whole idea of the world, we talk about modular, pre-manufactured, all stuff. We could pre-manufacture everything for this install, right? All the way to the window trim. That's efficient. All you got to do is learn the technique.
Perfect, thank you. And comment in the chat, thank you for the detailed responses, James. So,
well, I'm kind of wired that way.
A couple other questions here. The mock, oh, that was more of a comment. Okay, thoughts on Tyvek versus Siga Rothoblast, other exterior air barrier products on overall performance?
All good. Choose. If you want to use Rotoblast, you want to use MyVest, okay? Okay, whatever you want to use, it's fine. You can get, and I have on countless projects, passive house level air tightness with Tyvek, okay? You can do the same thing. For myself, I like Tyvek commercial. It's just robust enough and cheap enough. It kind of makes the builders I work with happy. If I start going to MyVest or other synthetics from overseas and stuff, they're a little bit more money, but the performance doesn't get better, okay? Look, when you buy the Tyvek, it's airtight. When you buy the tape, it's airtight. When you give it to the installer, it leaks. When I buy the MyVest, it's airtight. When I give it to the installer, it leaks. All the same things can happen. The key is the exterior insulation. You end up with little pinholes of air leakage, no matter what it is. But here's how it works. If I have what they call fish mouse, if I have a couple little fish mouse and it adds up to leakage in my building, but I'm going to put exterior insulation on, I'm going to put a sheet and compress it against that air barrier. Is it going to get more airtight or less airtight? Well, it's called the sandwich effect. It gets more airtight. So by doing the things in the order I've described for this webinar, you actually supplement the previous layer. You're not harming it. When we build the way we currently do, and we stuff walls and all the rest, we're completely reliant on water penetration resistant, a layer of membrane, and our wall. It doesn't make any sense because the wall's cold. It can condense like I talked about at the start of the webinar, okay? So another long answer, but to answer your question, yeah, they're all good.
Perfect. And then what are your thoughts, peel and stick versus mechanically fastened exterior air barriers?
Well, I have no problem with either one. Here's the deal. If you do something like a soaper stick VP or any VP permeable Grace, Henry, whatever, the peel stick vapor open on the outside, it can be more airtight. And the reason for this is if it gets damaged, it's stuck to the wood, right? And so even if I put it on the wall and I hit it with my hammer and make holes in it, it's still airtight. It's still reasonably watertight. But if I do the same thing with a loose layer mechanically attached, it can promote air leakage, okay? But at the same token, if I put exterior insulation, I'm going to sandwich the thing down anyway, okay? So, and no water can get past there. So you can think about where you want to spend your money, what type of job it is, time of year, what the trades are and the rest. And if you want to go for the extra bang for your buck, go with the VP. The VP is a little more challenging to install, okay? And you kind of need to slow down and have a process. I have a process for that, and I didn't share that for this webinar. But the thing about VP, and I even have my own projects, when you mess it up, how do you fix it? It's stuck to the plywood, right? So you got on and forgot to leave it, it's all negative lapped. Now what are you doing? Okay, so you might have an official that will give you a hard time. Now there are techniques that can prevent that from happening, but I find that many times it does happen. And so it's not a big deal. I don't have a problem with either one. Both of them I have used to reach exceptional airtight levels beyond passive. I mean, builders I've trained and worked with, they call it, I got 0.2, 0.3, 0.6, always less than 1. If you identify and make a reasonable effort to address transitions, interfaces, and process, you will always have less than 1 air change. That's it. It's not that hard.
Perfect. Thanks. And we do still have kind of some questions come through. So folks on the call who are like, wait, how long are we here for? We scheduled this until 10:15. So we have 15 minutes left. So if your questions keep coming through, that's great. We love this discussion. I will answer all the questions that come through. And then if there's time for James to look at the mock-up, we will do that. Okay, so a few more questions here. Do you ever use stainless steel fasteners versus standard U2/GRK for the strapping to gain an extended service life and a little less thermal bridging?
The amount of thermal bridging is very, very low compared to thermal clips, okay? With respect to service life, the answer is yes. And that would be, for example, in a marine climate, okay? So if I'm in a marine top climate, which is more corrosive top climate, I may opt for the stainless fasteners. But I also try to always opt for fasteners that are going to give me at least 1,500 hours in a salt spray test, okay? So they are highly corrosion resistant, okay? And whenever you do exterior insulation, one of the things that's really important, and it gets overlooked a lot of times, is it's always strapped and got venting. So you get this natural drying out, okay? And so it's not really an issue, okay? And so depends on what you want to spend. I know the U2 fasteners are GRKs because the same guy that worked and invented GRK started U2. They branched off. So you spend whatever you want, okay? I use U2s myself, okay? All the mock-ups you saw, they're all done with U2 fasteners. You can use whatever you like, okay? But if you have a marine climate or a corrosive type of climate, then yeah, use a stainless. You will get a little bang for the thermal conductivity or lack thereof. But you got to remember, you put the screw most times every 12 inches on center because the claddings aren't that heavy, okay? It's just not a lot. I mean, we're building walls for 100, well, not 100 years, but for decades with studs running through them, okay? For the love of God, with a 23% framing factor, okay? No, this has completely changed that game. We got continuous insulation on the outside.
Great, thanks. What are your thoughts on using foam insulation on retrofits, EPS/XPS versus mineral wool or wood fiber?
That'll be completely contingent on the amount of insulation that you put, okay? One of the things that's important to understand is the general vapor drive and direction is inward to outward. Typically, vapor drive follows heat flow, okay? And so you start to look at that and say, okay, if I put foam on the outside and I don't have enough to keep my sheathing above dew point, you got to ask yourself this simple question: how can it dry out? So it can't dry out through the foams. I mean, EPS is okay up to around 2 inches. It's got, just over perm. It's greatly reduced drying, but it can dry. XPS, no. Okay. GPS, graphite, polystyrene, okay. Part of the thing that I look at from a fundamental, and this is about building science fundamentals, if I have a drive drying and it wants to go this way, everything I put in the path of that is going to be conducive to that end result. So why would I put something that's going to slow down what it naturally wants to do and potentially cause lingering moisture where my organics are located? Now, if I put enough on the outside and I do a simple, you can calculate your sheathing temperature on a napkin kind of thing where you can take your overall R value inside, outside, divide the outside by the total. It'll give you a temperature drop. And then you take your design temperature and you subtract the two. It'll give you a rough idea what your sheathing temperature is. If you're falling somewhere around the 4 to 9 degrees area like that, okay, you're not going to have condensation. The whole idea that I fail at, and I'm not going to buy into the marketing and the sales and all the rest of it. I'm only going to go with the science. Is I'm going to build a wall whenever possible that I keep the sheathing above dew point. And I'm going to build a wall that's going to put and allow that drying to take place. And I'm going to build a wall that's going to be fire resilient, which is not foam. Okay. And I'm going to build a wall that has climate adaptation and will survive the 2050, 2060, 2070 temperature change we have, which means I'm going to put that extra layer of mineral wool on the outside. Now, if I want to, and I want to go low carbon, I might put wood fiber and cover that with mineral wool to get the fire resiliency, and I can get a low carbon hybrid wall. Lots of things I can do. You can do foams. They're not fire resilient. Okay.
Okay, so many different considerations. Thank you. All right, our last question here, unless folks have anything else they want to pop in the chat or they can raise their hand. Just a comment on this person has seen increasing numbers of homes using ICF for their envelope. So just asking if you can comment on this and what are things to look out for.
ICF by fundamentals can work just fine. Okay. You have limited flexibility, difficult to make changes. Water penetration at windows can be a challenge. You might want to run a full membrane on the outside of the ICF and treat it like a standard frame wall. That will be some of the guarantee requirements. I mean, there's water stops and all kinds of stuff you do. I have no problem with ICF. We have to look at all things, though, a little bit holistically, okay? It's not the best for carbon. No, they're working on that, okay? And so low carbon concrete and all the rest of this here. It just struck me. I just did a project with some BCIT students. I served as a mentor, and they work in the ICF industry, and you get all the inside stories about the blowouts and the missed cans and the coring after and all the rest of it. And it does lack flexibility that wood framing doesn't have, okay? Now, I have no problem with ICF whatsoever. It can work just fine. Even if you have a fire, the foam burns, but the concrete stays, but the heat can damage the concrete. So you might have to tear it down anyway. So you need a structural evaluation depending on what kind of heat it was exposed to. It becomes dicey. I know that if I build a wood frame wall and I put the mineral wool on the outside, and I built this in my property, and I do this kind of testing, and I tried to burn down these walls. And I put combustible cladding on rain screen on mineral wool on Tyvek on 2x4 walls, and I burned them to the ground to the point where the strapping was gone. Okay. The only thing left was just charred mineral wool. I took the mineral wool off and the Tyvek was perfect. And so I say to myself, why am I going to mess with a good thing? All I got to do is enhance it. So I've done the same thing. I solved for decks, soffits, and I'm in the middle of process designing for windows from fire resiliency, all using just standard products, okay, and a little bit of different technique, and none of it has foam. That doesn't mean I don't like foam and it won't work for the fundamentals. Of course it will. But fire is being looked at even to building code level, where depending if you're a wildfire urban interface area or high risk area, you can't build with it anyway. And so everything's going a little bit down a different pathway because the catastrophic loss providers in this country are sick and tired of paying out catastrophic amounts of money. So that's what triggers change, okay? And change is coming.
Great, thank you. And yeah, you heard that right, folks. James likes to spend his spare time lighting walls on fire out in Meadow Creek.
Well, I live very remotely in the middle of nowhere, and I have a large gravel parking lot and a water cannon. So I just let her go. Yeah.
Perfect. All right, James, we have about 7 minutes left. Is that enough time to kind of look at a couple things with the mock-ups?
I can be happy to take it apart or show the mock-up, which is going to be used as a carpentry students' term project. So when they graduate, they'll be able to bring everything to site ahead of time because they know the rough opening sides. Okay, so what I'm going to do is move you over here. This is that same mock-up that you saw in PowerPoint. Okay, this is the bunk sheet. You see how that it wraps around at the end dams? And what it does is provides insect control and also what's known as an ember guard. So houses catch fire from flying embers, and if they're flying to hit your wall and they go through this little shoulder hole, which I see a lot of times, then how are you going to get that closed? So this bunk screen helps do that effectively. This is that same perforated aluminum. Right here, just cut it, bend it, fasten it. Quite simple. That's how the strapping comes when I get handed on site. Screws in it, place it into place. These are the wind devils used to fasten it that I showed you. Here's the membrane. Here you can see that I have the heel stick that I can take this strapping off anytime I like and change it if I have any damage. I've left the release on here, but the release is off all here. You can see the score line right there. And I lap it over just to cover my fasteners, and I have a shingle application. I can take the trim boards off. I'll show you the back. You can see here is back cut curve. This here slides onto my end dam. You see that my end dam is folded back to meet the plane of this strapping for the back of this sits. So this just sleeves right into place. And it's very neat. 1 inch notch allows for what I'm doing, and everything fits perfectly. And same concept. It's the same cut. I just cut this notch out with the board upside down, and this happens automatically. It's like, it's kind of an open. Now I'll take the trim off on a return. Here I'm using a fine screw made by YouTube, but it's a very fine screw. Allows you to see you can see the banana bread. It's tucked into the opening right here. Okay, and that goes all the way around on both sides. And I get to make the sill flashing. One of the things that's important is this wood trim is actually mainstream, even though it's returned, and I'll explain how that works. This here strapping and this strapping is actually set 1/4 inch proud of the insulation. So when I mount my trim, I have a drainage space all the way down. Lands on the sill under here where I had that pan membrane I showed you, and then drains out. So I have rain screen on all sides. The same with the head. The head sits down, any water would come along, down and out. It's fully drained. You can see the flashing of the sill is attached to the side here with a pan screw. And I put another pan screw up here so that when I put the trim on, it sits planar. You see the same gap all the way along because the end dam takes up a bit of space. So I put a screw right here, and it's a leveling screw. So it allows this to go on. All the trim everywhere
has a gap for ceiling. All the way around, so by part 9, you need to cut between the window and your cladding. So I leave a gap this way and I seal this way, this way, and this way. So when you're looking at it, you don't see it. Then I have a 1/4 inch gives me enough for 1/4 by 1/4, 1-to-1 ratio is allowable by way of seal profile for durability. One of the biggest failures I see on warranty reviews that I do is fail sealing around windows because you put the sealant on, then lick it with the finger and you get this little micro bead of sealant around there. It's like an elastic band. See, if you don't have any center thickness, if you hold an elastic like this, can you pull it apart? No. No. But if I leave a little gap, all of a sudden, oh, I can move it. Larger gap, oh, I can move it. Well, if your sealant doesn't have a little bit of center thickness and there's movement, it splits. That's what happens. You can't finger lick it, not Kentucky Fried Sealant, okay? Not your finger licking good.
Thanks, James. I just wanted to let you know we've got a minute till the end. I'm happy to have this
Okay.
extend for a few more minutes if you want to finish this up.
I'll shut it down now, if that's okay. I'll just
All right.
This is just showing the end dams. I pre-drill them. They go in, you can see the banana bread goes all the way around the window. I got little red arrows, that's my drainage point, for instructional purposes. And the rest of it, I showed you the membrane works. And that's it in a nutshell. All of this can be pre-made from the knowledge of the rough opener. That's it.
Perfect. Thanks, James. I'm glad we had a few extra minutes to go through that. And thanks everyone for joining us this morning. I will send out an email with a link to today's recording, along with a link to part 1 if you missed that. Yeah, so thanks for taking out some time in your morning. Thanks for joining us, James, and sharing your knowledge with us. And we'll see you in the new year.
Thanks, everybody. Thanks for the questions. Love it.
Take care.